Master, good afternoon. There was this question someone inboxed me about the resistance RT of a platinum wire temperature small t measured on a gas scale is given by RT is equal to R naught into 1 plus AT plus BT squared, where A is equal to 3.8 times 10 to the power negative 3, and B is equal to negative 5.6 times 10 to the power negative 7. What temperature will the platinum thermometer indicate? What temperature will the platinum thermometer indicate? When the temperature on the gas scale is 200 degrees Celsius. Now, according to that question, we are expected to get the temperature small t from R at unknown temperature minus R at ice point out of the resistance at steam point minus the resistance at ice point times 100 degrees Celsius. So go ahead and investigate. The resistance at unknown temperature is the resistance when we have temperature is equal to 200, which can be got from R naught into brackets 1 plus 200 A plus 200 squared of B. And at this note, you'll have R at 200 as R naught into 1 plus, the A is 3.8 times 10 power negative 3 times 200. Then plus the 200 squared gives us 40,000 times B, which is a negative 5.6 times 10 to the power negative 7. Therefore, the resistance at 200 would be R naught into brackets 1 plus 200 times 3.8, you get 7.6. So 7.6 times 10 to the power negative 2 plus, now this is a minus, 4 times 5.6, 5.6 times 2 gives us 112, which 112 times 2 gives you 224. So you get 2.24 times 10 to the power negative 3. When you confirm with the calc, those must be the answers. Then at 100, which is steam point, we shall have R naught into 1 plus 200, sorry, plus 100 times A plus 100 squared times B. And this resistance at steam point would give us resistance at ice point into 1 plus 100 times 3.8 times 10 to the power negative 3 plus 10,000 times negative 5.6 times 10 to the power negative 7. So this will take me to R naught into 1 plus 3.8 times 10 power negative 1 plus minus 5.6 times 10 to the power negative 3. Therefore, small t would be, since we have seen it is R at T, which is R at 200 minus R at ice point over R at steam point minus R at ice point times 100 degrees Celsius. Then this would realize R naught 1 plus 7.6 times 10 power negative 2 minus 2.24 times 10 power negative 3 minus R naught. All this is divided by R at 100, we have realized is R naught into 1 plus 3.8 times 10 to the power negative 1 minus 5.6 times 10 times 10 to the power negative 3 minus R naught times 100 degrees Celsius. So more of patience is required in such numbers so that you can subtract off this one. 1 times R naught gives you R naught. So you will have R naught minus R naught. R naught minus R naught. So when you subtract, you realize that you can actually divide off everything by R naught when you factor and simplify. So the numerator remains with 7.6 times 10 power negative 2 minus 2.24 times 10 power negative 3 divided by 3.8 times 10 power negative 1 minus 5.6 times 10 power negative 3 times 100. Can you compute and give me the answer? That will give us the answer. So those of you who had challenges with that number, that is how you had to go about it patiently. In other words, if you never wanted to substitute for the A and the B in the beginning, you could go for the A and the B and you simplify up to the end, then you substitute the A and the B later. So when you have that down, you're going to also have the thermoelectric thermometer. So press your calc and give me the answer. So that was a number that was accompanying the electrical resistance thermometer. That is the thermometer, that's the platinum resistance thermometer. I have to show you how it goes about it. So have it down.
19.7 degrees Celsius.
19.7 degrees Celsius. Okay. That is our answer. So they just require patience in such numbers. You don't rush them. You give them some ample time as you try them out. So this next one, I can now go for it. This is called the thermoelectric thermometer.
You have not returned. Charged by government. What? Only for 4 years, I think. Since I kept on working.
So this one is called the thermoelectric thermometer or the thermocouple. It's called the thermocouple. And the thermocouple uses a physical property, which is the change in EMF. Change in EMF of a metal when the temperature rises. So when the temperature rises, there is a change in an EMF that is induced in a thermocouple of two disjointed wires or dissimilar wires. So this wire can be for copper, even this can be for copper. Then this one can be for iron. And these wires can be joined here. So that's a joint for the two wires. Then this is pure melting ice. Pure melting ice. So one junction is placed in an ice water mixture, then the other junction is placed in the surrounding where the temperature has to be measured. So you will find that the thermometer depends on the linear change of two metals joined together when the temperature rises. And the measurable physical property I've mentioned here is the change in EMF of a metal when the temperature rises or increases. And with that, the expression which can predict the temperature theta in degrees Celsius can be predicted from theta is equal to the EMF at unknown temperature minus the EMF at ice point divided by the EMF at steam point minus the EMF at ice point times 100 degrees Celsius. So this is the mathematical expression that can help us predict the temperature using a thermocouple. And we have said the thermocouple is basically using EMF. So where E theta is EMF of metals at unknown temperature, then we have E naught is EMF of metals at steam point, at ice point. Then this is E100 is EMF of metals at steam point. Then on a thermodynamic scale, that is the Kelvin scale, we can have the temperature reading from this expression, where capital T can be got from EMF at triple point out of EMF, sorry, EMF at unknown temperature out of EMF at triple point. EMF at unknown temperature over EMF at triple point times 273.16 Kelvin. So this is on a thermodynamic scale, where ET is EMF at unknown temperature then ETR or ETP is EMF at triple point. Of water. So, if we mention its construction, how it is designed, how it is brought out, it's made up, or it consists of two different metals, just like this illustration. The metals here are different. We have copper and we have iron. Those are two different metals. Such as copper and iron joined in a circuit, and their junctions kept at different temperatures. So this temperature here, it can be theta 1, this one can be theta 2. So they are both kept at different temperatures. The difference in temperature causes an EMF to be generated. the current flows. So because the joints have different temperatures, they will induce an EMF through the wires, and we shall have a current that flows. The ends are connected to a galvanometer, which deflects or detects the EMF. The galvanometer is it has a nib which deflects when it detects current. Some of you, if you've seen your father's cars, there's where there is that, the mechanics call it HSL, but there is a point and a reading for the speed, for the temperature, for the speed, temperature, and the gears, I think. So those items use a principle of a galvanometer. So they do deflections. So a galvanometer deflects whenever current flows. Whenever current flows, we shall have a deflection in the galvanometer to the left or to the right, depending on the design of the galvanometer. So even here on this thermocouple, there's a galvanometer connected, which will always deflect whenever a current is detected. So any detections of current that can be seen, they will lead to the deflection of the what? Of the galvanometer. Oh, how it works? So that's the construction. That is how it is built. Then how it works is the junction, the hot junction is put in an ice water mixture at 0 degrees Celsius, and the EMF E naught is determined. So you get this junction here, because this one is initially in an ice water mixture. Then you place this one, it is the one which is variable junction. This is the variable junction, the one you use to detect other temperatures. So you get it and put it in an ice water mixture and read the temperature E naught. Then the hot junction is put in a point whose temperature is required. So you go ahead and put it in an environment whose temperature E theta you are looking for. Then also, as a result, there will be a difference in the temperature, and the thermal EMF will be generated, which thermal EMF will bring about E theta and E naught. Then it is also put in a steam point, or in a steam system or vessel, and the EMF E at 100 can be attained. When it is determined, the unknown temperature can be got from this expression, of which those notes and write up I'm going to send, and you can have them noted down, and you see how effectively it operates. Now, one of the situations, but when we put it in an ice water mixture, the EMF it will read will be 0. So if the EMF read is 0, then that means the temperature can be got from E theta out of E 100 times 100 degrees Celsius. If it reads 0, it means that EMF at ice point, when it was detected, it predicted at 0 EMF. So whenever you come up across an illustration which is of this kind, yeah, then it would mean that the EMF at ice point was 0 at that instant. Otherwise, if it's not 0, it will always remain in this state, and you'll have the EMF at ice point, which you substitute here and there, and then you can come up with the expression for whatever you're looking for. This experiment also has a graph. So there is a note in the notes. You will see that when the hot junction is put in an ice water mixture, the temperature at both junctions is the same. You know, this was theta 1, this was theta 2. Where this junction, which reads theta 2, is, when you place this junction in another ice water mixture, the temperature will be the same. Because if the temperature here is 0 degrees Celsius, even this side, when you put it in ice water mixture, will be 0 degrees what? Celsius. So the change in temperature will be 0, which change in temperature becoming 0 makes the EMF at steam point also be 0, because the EMF changes as a result of change in temperature. Therefore, with that note, we can have the graph of variation of EMF with temperature. Variation of EMF with the temperature. This variation takes a shape like this one, whereby if this is temperature, and this one can be our EMF. So for that note, the graph looks like this. This is what we call the neutral temperature. So we have what we call a thermo junction, which I've talked about here in the write-up, whereby it's one that is formed by fusing the ends of two different metals. So this is what we call the thermo junction. I skipped another one. Okay. This one here, where the two metals meet, is what we call the thermo junction. Is one formed by fusing the ends of two different metals. When the joint is heated, an EMF is generated between the free ends of the two metals. So that's how this thermocouple works. Some of the advantages of a thermocouple are: one, has a small heat capacity, and this can be used to follow rapidly changing temperatures. So advantages: small heat capacity. Small heat capacity means, some of you don't know what heat capacity is all about. Heat capacity is the amount of energy you require to heat a given substance to reach its boiling point. And if you have a very low heat capacity or specific heat capacity, it means you require less heat energy to reach the boiling point of that item. So with that regard, it can easily work for very rapidly changing what? Temperatures. Then it can also measure temperature at a point. And measure temperature at a joint or at a point. Why? Because we have junctions which are built. Those junctions are built with the two wires. They can easily measure temperature at a point. You just get that junction and put it at a point you want to measure. Robust and compact. Cheap to make and easy to construct. How am I? And easy to construct. Then it also has some disadvantages. And among them, it can't measure temperature beyond the neutral point. Cannot measure temperature beyond the neutral point. And that one we have seen the neutral point, it's on the graph. The neutral point is here where we have the neutral temperature. Then it's not very accurate at very high temperatures. The second one is not very accurate. At very high temperatures. So those are some of its disadvantages. There is an example here we should look at. Let me take a screenshot and send it through, which is talking about the test junction. This is what we call the test junction, this one. This side is where we have the test junction. This one is a fixed junction. Does not change.
Yes, some people are looking for the same book. Say, instead of this things, you bring the books and bring us.
This is physics.
It is very well because I have the one.
Take the screenshot.
So the one you brought, and they are new, so they are not the so everybody goes in Malaysia. So it's simply part of the water. But when I make the assessment, that company made a lot of sense. So I told him assessment. So I took time to study and match some again.
Okay, here is the number.
So, and they also talk about this. And they are also independent. The topics were also independent. But the under one supervision.
I've sent it on the group.
Giving her safe passage because it told me this is very dangerous place.
Like say, we get the professor from Maryland. I done my best to write for us. We get the professor from Boston, Massachusetts.
By the way,
So here is a question. The question says, when the test junction of a thermocouple is placed in successfully in a water bath of unknown temperature, and then is in boiling water, it reads 1.44 millivolts and 4.00 millivolts respectively. Calculate the temperature of the water bath. So the first case, temperature of the water bath can be got from E at theta out of E at 100 times 100 degrees Celsius. The reason is why we have not used E theta naught minus E theta naught. It's because E theta naught, we saw that it gave us EMF as 0 because the temperature difference was 0 when we place the ice, when we place the junction in both an ice water mixture this side and also another ice water mixture on the other side. Because the EMF is induced as a result of change in temperature, here the temperature is the same. They are both ice water mixtures, so they're both having 0 degrees Celsius. So the temperature change is 0, it corresponds to a 0 EMF induced. That's why we ended up coming up with an expression of this kind. Now, according to what has been given, the readings when we have unknown temperature, E theta, the EMF is 1.44 times 10 power negative 3 volts. When the EMF is in boiling water, we shall have steam, which EMF is actually 4.0 times 10 power negative 3 volts. Therefore, when you substitute for theta, you will get 4.0 times 10 power negative 3 divided by 1.44 times 10 power negative 3 times 100. We can lose this with that, and then you simplify with a calc and give me the answer.
Two 277.78 degrees Celsius.
200. 200?
77.
Wait, did I substitute correctly? No, I didn't. Substituted wrongly. You know why? It is E theta up, then down you have E at steam point. So E theta is 1.44 times 10 power negative 3. Then down is 4.0 times 10 power negative 3. So can you try that again?
That is
That what?
36
36
degrees Celsius.
degrees Celsius. Correct. Then the second case, they're asking you find the thermometric EMF when the test junction placed in melting tin at a temperature of that. We have temperature is 232 degrees Celsius. We want the EMF E theta. We don't know. We are given E at steam, which is 4.00 times 10 power negative 3. So we shall have theta is equal to E theta out of E 100 times 100 degrees Celsius. This will take me to 232 is equal to E theta, which we don't know, out of E at 100 is 4.00 times 10 power negative 3 times 100. Finally, you would make E theta the subject to give us 4 times 10 to the power negative 3 times 232 divided by 100. What answer do we get?
Food is to our body what fuel is to an automobile. It contains
Someone press the calc.
the anterior opening of the alimentary canal.
9.28 exponent negative 3.
And actually, this is the same as 9.28. Sorry, it's the same as 9.28 millivolts. It's the same as that.
The hard chewing surface of the tooth made out of enamel helps in chewing
Okay.
and breaking down the food.
So the last type of thermometers are the pyrometers.
Two sets of teeth during their lifetime and are hence known as different. The problems teeth in adults are of 4 types. Incisors represented by I, canines represented by C, premolars and molars represented by P.
So the last experiment we need to look at is what we call pyrometers. Pyrometers. And the pyrometer is an instrument used to measure the temperature of a hot body by the radiations the hot body emits. An example are the usual pyrometers we use for testing COVID, those temperature guns. Those are examples of pyrometers. So they get the heat you emit from your body. So they use radiation as a mechanism of heat transfer. So they are best suitable for measuring temperatures above 100 degrees and above. And the wavelength of the radiation is the thermometric property used. So if we can predict the wavelength of the radiation of the heat you're emitting, then we can use that as the property to predict the temperature of the body. There are two types, whereby one is what we call the optical pyrometers. Optical pyrometers, and then we have what we call the total radiation pyrometers. Total radiation pyrometers. And the optical pyrometer, let me bring you the illustration. Sketching it might take quite some time.
All living organisms contain cells which require nutrients and oxygen to produce energy. Cells also produce wastes such as urea, uric acid, and carbon dioxide. Hence, there should be a continuous supply of nutrients and the removal of waste from the cells. This process of supply and removal is carried out by simple organisms like sponges, by allowing water to flow through their body cavities. It is also carried out by complex organisms like humans through a special medium called body fluids that circulate these substances throughout the body. Body fluids include blood.
So here is what an optical pyrometer looks like. The other and the total radiation pyrometer, we shall see it later. Now, it is made of, for example, this is the source of the heat. The hot body is right here. So radiation is focused onto an objective lens, which focuses the beam of radiation. And then it is going to be absorbed by this tungsten filament. This is a tungsten filament, a hot metal, which cannot easily reach its boiling point because it's a hard metal. And then after which it will be subjected to a filter, which filter now will take it to the eyepiece, and then someone can be able to view the radiation. It can be in form of light, whereby it can be visible. So if that is the illustration of the optical pyrometer, this is how it works. Thermal radiation from a hot body is focused on the lamp using the objective lens. So the lamp is this one, a filament lamp. Radiation from both the hot body and the filament lamp is passed through a red filter at a known wavelength. So the filter is here. This filter has a range of wavelength, which is known. Then the observer looks through the eyepiece lens to observe the image of the hot body and the filament against the background on a smaller area of the body. So the observer right here. So the observer here views the image of the filament lamp. If the filament appears bright on a dark background, the filament we see here, if it appears bright on a dark background, then the hot body is less bright. But if the filament appears dark against a bright background, then the filament, the hot body is hotter and brighter. So that is what that statement here says. We are saying if the filament appears bright on a dark background, then the hot body is less bright. But if the image of the filament appears dark against a bright background, then the hot body is hotter and brighter. So it means the hot body now is bright and hot, this lamp, of course. The current through the filament is adjusted. So we adjust this current using a rheostat, which is here, until it appears bright as the background light from the hot body. So we adjust it until it appears bright, like this hot body we have here. Then the temperature of the hot body is then read from the ammeter and calibrated in kelvins. So the temperature can be read and the current that is flowing through the ammeter. Sorry, the current flowing through the ammeter is read and then it is calibrated to give the reading of the temperature in Kelvin. And with that, we can be in position to predict the temperature of the given hot body. By that, you are using what we call optical pyrometers. So therefore, allow me send notes on the thermocouple, the electric thermocouple, which I've discussed, and I've also discussed the the optical pyrometer. For the optical pyrometer, I've already sent, that is, those are the notes. I've seen 4 people. I don't know whether all of you are on the group. I think you're all there. So allow me to send those other notes. So next time, we are going to introduce a new item, which I can't start now. The new item we are going to start off with shall be heat capacities. Yeah, heat capacity and specific heat capacity. So you read about heat capacity and specific heat capacity. So we have finalized with thermometers as we had introduced them. Unless if someone has a question. If no questions, let me take these screenshots for the notes and you have them so that you can have
Teacher,
some.
instead of drawing the full circuit diagram on the filament, it's okay if you just draw that upper part where you draw a circle and wires.
Instead of drawing, and you draw like this, the galvanometer. Sometimes some people draw with an arrow. Then you draw. And you just draw only that.
Teacher, on the diagram, which is on the screen of the optical pyrometer.
Instead of doing what?
Drawing that full filament with a circuit.
And you just.
It's okay if you just put the filament just.
Atkat now, the challenge is you'll have to talk about the rheostat to adjust. You also have to talk about the ammeter, which will predict the current flowing at that instant. Then they calibrate that current to give a reading in Kelvin. I think we need to have it there because we are going to talk about it. Otherwise, chances are very high that some of these items, when you miss them in the diagram, you might end up forgetting to talk about them. Okay? That is my only worry. That people might forget. Some remember and talk about them, but other students forget about them totally. Budget meeting. Okay, so with that, I think we can call it a day because our time is up. So read about heat capacity, the same heat capacities you had in O-level, and specific capacity, though we shall advance a little here at A level. Okay. Have a good day.